So let's start again. So for the coming 45 minutes, I will give you a brief introduction to nuclear energy. It's a difficult task where I myself, doing my master's, I basically went through a full educational, like a master program about nuclear engineering. So to boil 2 years of master's into 1 hour, or even better, 45 minutes, is not an easy task, but we see what we can do. As after the usual introduction, we will see what are the basics of like the physics behind nuclear energy, which I think is the most interesting part, but it's also the part that it's needed, the minimum that it's needed to know to understand why nuclear power plants work in a certain way. After that, we will see how nuclear power plants work and a few types of them. So, going back to some more serious stuff. Today there are around 450 power reactors in operation in the world for a total installed capacity of nearly 400 gigawatt. You all probably know that the nuclear history has had a lot of ups and downs, depending on more or less ups when oil prices became particularly high and downs after nuclear accidents. What are the future trends? Well, we see again quite a different situation in which in Europe and US we are going a bit towards a phasing out from nuclear, while in other countries, particularly China and India, but we're seeing a lot of new nuclear power plants built. In particular, there are 52 power plants that are expected to be built until 2026. When we look about the reserves, uranium is expected, if we keep consuming it at this rate, to last for around 70 to 80 years. Knowing that if prices of uranium were to double, then there will be more resources available that can be extracted at a like convenient price, that would basically double this duration. What are the pros of nuclear energy? Quite a lot. First of all, we have very low CO2 emissions. Basically, almost only those related to the construction of a plant and of the decommissioning of a plant. We have no pollutant emissions to air. We don't have combustion, so we don't have ashes, we don't have particulate matter, sulfur oxide, all what I've talked about before, we don't have it. We have very low, relatively low operational costs. Why is this an advantage? It is an advantage because it means that if I build a power plant today, a nuclear power plant today, and tomorrow the price of uranium fuel doubles, I don't care. I don't care because basically more than 60% of the costs related to uranium, like the nuclear power plants, is related to building the plant and then dismantling at the end. So the fuel itself is not expensive. And this is important because many prices fluctuate, but if uranium fluctuates, we don't care. In addition, fuel for uranium is not so widespread, so it's not like coal that you find a bit of it everywhere, but it is located in very, let's say, safe or stable countries. Most of the reserves worldwide are in Australia, then we have Canada and Brazil that are very large producers. This means that we don't have to fear that at a certain point the war is going to start in a place, and then our uranium supply is going to stop. Finally, we have the potential for alternative fuels. I will speak about the potential for fast reactors and the use of uranium-238 later. But to make it to boil it down to a major point, there is technology today that is not really used, but it is available and that has been proven that could basically make our uranium resources to last not 70 or 80 years, but 700 years. Why not nuclear energy? Unfortunately, we have a lot of points here as well. The most known one, of course, is related to accidents. They don't happen very often, but when they happen, they are bad. Three Mile Island was the first one in the United States, didn't cause much damage, but then we had Chernobyl, 86, big damage in Ukraine, and then some years ago Fukushima in Japan, and all of them have been quite bad. The second most important thing, and I would say that at least from my own perspective, is the most important thing, is what we do with spent fuel. We'll see later on, fuel that is basically used by a nuclear power plant and that we have to take it out and to do something with it, is very radioactive, so very dangerous, and it's gonna stay very dangerous for about 1 million years. So we have to think of a way to store it somewhere or to deal with it and to keep it safe for 1 million years. That's like beyond the scale of how long humanity has existed on Earth. So I mean, that's a long time. And today there is no real solution. So we don't have at the moment one solution that we know that works. Capital costs are very high. You don't build a nuclear power plant in your garden. It's stuff that is like 1 gigawatt the size normally. Then it depends on the type, but as a matter, just to give an idea. So it is a very long-term project, state-owned business, and the problem is that there is a bad record of cost overrun. So even if the investment cost is already high, normally it even gets higher because something goes wrong when you build it. And then it has a high operational inertia. That means that we have a low margin for regulation. You will see better about this when you look more into renewable energy. That has the opposite problem in the sense, well, it is the same problem in a different way. So while renewable energy normally is randomly shifting, so you don't really know when you're going to have sun or wind, and you cannot really regulate to what you actually need. The problem with nuclear power plants is that you can't say, oh, tomorrow, in next hour, I have a high demand. Let's switch on our nuclear power plant. That's not something you do. Nuclear power plant takes 1 day to switch on and 1 day to switch off, and the possibility to regulate it are limited. So that means that from the electric grid point of view, it's quite demanding. Just a side note about when we talk about nuclear safety, I found some statistics about the mortality rate per unit of energy produced. So how many deaths have been generated because of different reasons for generating one unit of energy that is in this case a very large one. And from this we see that of course nuclear accidents are bad and they generate a lot, they gave a lot of problems and they tend to also kill people, unfortunately. But when it comes to the fact that they are very rare and they are connected to something that generates a lot of electricity, when we look at the history, in itself nuclear power is not very dangerous. Of course, this is only looking at deaths. It doesn't, so it's a very limited perspective, doesn't look at the damage to the environment. It can be a skewed statistic. Here I say, for example, we see that hydro has a lot of death. Like, how can that be? People falling off from a dam? That's not, there has been one accident in history in China where 170,000 people died, which completely skews the statistics. So I mean, these numbers have to be taken with care, but when you hear that nuclear is dangerous, just remember, think it through, because it is true to a certain extent, but other sources of energy are not necessarily that much better. So, the core and, let's say, the tough part about this lecture is looking into the physics of how nuclear power works. When you do combustion, you tap into the chemical energy content of a fuel. When you look into nuclear energy, you're actually looking at you're looking at the nuclear energy, so the strong force that binds the nucleons, so the protons and neutrons inside nuclei. How does that work? So here, have you ever seen this graph before? Raise your hand if you have. Okay, very well, at least some. So the idea is that here is the number of nucleons in the nucleus, so like the more we go on the right, the more we go from light elements, so you see there hydrogen, helium, etc., to heavy elements. And on the other axis, you have the average binding energy per nucleon, which is basically the average amount of energy that you have to spend to take neutrons or like nucleons away from the nucleus. And you see that the shape of this curve, even if it's a bit like sometimes random, but it has like a peak around the element of iron, and then it goes down. So, like to boil it down a bit to the to what is important to know here is that if I go more on the right compared to iron, I go towards less stable nuclei, and that means that if I took apart all the neutrons and protons in a nucleus of uranium and I rearrange them to become all of them just iron, I will get a lot of energy out of it. Because the iron is more stable and the difference is the energy that I gain. How much is that? You can see basically that difference. It's the small red arrow on the right. I won't go through the units conversion because it's in nuclear energy you normally use this unit called the mega electron volt, which is a bit tricky to convert. But all in all, it means that if we simply took like 1 kilogram of uranium-235, its corresponding value, so the energy that is released once that has all reacted after nuclear fission, is around 76,000 gigajoule per kilogram. As a reference, you can see this figure. Gasoline has 46 megajoules per kilograms, while uranium has 76 million. Sorry. And the bottom line from this comic is that the log scales are for quitters who can't make their point properly. So that is the idea. So there is a lot of energy over there, and that's what we go and look into when we look into nuclear energy. I now go and do a very, very short digression to basically answer one thing that maybe you know already, or maybe you have at least wondered when looking at this figure. So why go all the way to the right, where there is like this small difference between uranium and iron, and why not stay here? You see, this is hydrogen, and up there you have oxygen. So here, there you have like 0.9 mega electron volt. On this side, you have like 16, just going from hydrogen to helium. That is called nuclear fusion. That is the power that powers up the sun and the stars in general. And that is something that we have been doing research, like we as humans have been doing a lot of research into, not we as our group, unfortunately. Can human make nuclear fusion happen? Yes. First, it has happened in prototype nuclear reactors, but I would say that there has been one way in which we have been very successful. I don't know if you have ever heard of a hydrogen bomb, but it exists. It's still the most powerful bomb that has been ever created by humans, and it basically uses nuclear fission to generate nuclear fusion. And it's something that we don't really want to see, but that's a way that humans have been able to use nuclear fusion. From a more like a peaceful perspective, there have been many efforts, a lot of money involved. The European Union has been running this ITER experiment for quite a while. It's a reactor in Cadarache in France. The bottom line is that while there are many ideas and theoretically can work, in practice we have not one single reactor, even experimental, that has been able to sustain nuclear fusion for a reasonable amount of time. And when I say reasonable, I mean at least a couple of hours. Now we're talking about seconds. And no ever fusion nuclear reactor has ever been able to produce more energy than it is actually used. Some people say it's 20 years away. Some people say it's 50. Just to let you know that it exists, it would be awesome if it worked, but we are not there yet. Okay, back to fission. So we want to basically break apart one atom of uranium to split it and to make it become smaller ones, because we know that the smaller ones have a lower energy per nucleon, so we can get energy out of it. So how does it work? Well, basically, we the normal way to do it is that we send a neutron towards one atom of uranium, or nucleus of uranium. The nucleus of uranium becomes unstable, and then it breaks apart. It breaks apart normally in two or more smaller nuclei, and a variable number of neutrons that are basically shot away at high energy. Most of the energy of the reaction goes into those nuclei, and particularly in kinetic energy. So they are basically like also shot at very high energy, at very high speed, and then start to bounce off against other stuff in the nuclear in the rod, so in the fuel element. And by doing this, they transmit the energy from kinetic to other particles, until it basically generates, that is macroscopically seen as heat. So that generates the fact that these nuclear bars becomes very hot, as you've seen from The Simpsons. The rest of the energy is not very interesting because, first of all, it's a small part of it, and secondly, because we're not necessarily able to take it. What is interesting is the energy that goes into the neutrons, because they are emitted at high energy, and we have an average for a uranium-235 reaction, an average of 2.5 neutrons per reaction, which is interesting because we need at least one to sustain the reaction. So if we want one reaction to generate enough neutrons to make another reaction, we need at least one more neutron. So as I said, we get one neutron into a very big nucleus, and that nucleus becomes unstable. So sounds easy in principle. In practice, is quite a difficult process for a number of reasons. First, what happens? We have to keep the reaction chain going on. So the nuclear reaction chain going on. What happens if for every nuclear reaction, so for every fission, if we have fewer fission events that happen later? Then basically the reactions will die out and our reactor will shut down. If on the other hand we have more new fissions at every generation, so every time we have fissions, new neutrons, more neutrons, again more fissions, etc., then we get a supercritical reactor, which is, when you're talking about steam, supercritical is good. When you're talking about nuclear fission, supercritical is bad because it's basically a bomb. So it means that when the number of reactions is going to increase until the whole thing explodes. Not good. So what you want is that the number of fission remains constant from one generation of neutrons to the other. And as you can see, even if the number of the unbalance was small, over time it will become large. So it has a difficult thing to control. So we have to sustain the reaction, but it means that we need to have enough neutrons and enough neutrons that are able to generate fission. So we are getting a bit more down into the details, but it's important. So we said that our uranium nucleus gets one neutron, right? How do you do that? It's not like playing basketball that you just like throw the ball into something and then it gets somewhere. There has to be the nucleus must want the neutron to come in, basically. The unit, we have like a type of unit in a sense that a type of indicator that tells us how much a nucleus is happy to receive a neutron, and this is called the cross-section. And you can see from this figure how the cross-section of what you should look at the green one, which is uranium-235, which is the most common nuclear fuel. And on the x-axis is the energy of the neutron. So you can see that the neutron is emitted at those energy, where the cross-section is around 1, while at low energy, which is more or less at the energy that the neutrons have when they are in equilibrium with the rest of a reactor, then this cross-section is much higher. So the idea, and that is what basically almost all nuclear power plants work today, is that we have the neutrons that are emitted at high energy, and we want to slow them down. Slow them down until they have they basically start to go slow enough for the nucleus to catch them somehow. How do you slow them? Well, there is an element like that we use in, like the definition of the element that we use to slow them down is a moderator. We need that it has high probability of impact. It must have a mass as close as possible to a neutron, because then it's easier to slow something down. And it must have a low probability of capturing the neutron. So you want basically that the neutron hits the moderator and bounces off with lower energy than it started, but is not absorbed. If you combine all these three characteristics together, we end with three main candidates that are used today, have been used also in the past. Hydrogen, well, we said before that we want something that has more or less the mass of a neutron. Well, hydrogen has almost exactly, the nucleus of hydrogen has almost exactly the mass of a neutron. The main problem, it would be perfect if not for the fact that hydrogen likes a lot to absorb neutrons. So if you have hydrogen, that means basically in practice light water, that is normal water, as a moderator, it will absorb your neutrons, and you're not happy about it because you don't have so many. So what other people started to think was like, oh, why don't we use deuterium? Deuterium is still hydrogen, but with one additional neutron in the nucleus. So it still works quite well, but it doesn't absorb neutrons. So yay, very good. But the problem is that deuterium that we normally use in the form of heavy water, which is just water with deuterium instead of normal hydrogen, is expensive. And finally, we can use carbon, and that's like some nuclear reactors are moderated using graphite. That's basically what you use to write if you have a pencil, and you are old-fashioned like me. So carbon is a bit worse than both of the others, but it still works. And in the end, it has been used for a while for other reasons. Now, I want to go first, before I start to tell you how a nuclear power plant works, I want to go quickly through the nuclear fuel cycle. Why? There is a specific reason. If we go quickly through the initial part, in which I extract uranium, we basically concentrate it and make it like this kind of condensed form. It is a UF uranium with 6 atoms of fluoride. And the next natural step that happens for basically almost all power plants around is the enrichment. You've probably heard before of enrichment of uranium if you are at least a little bit interested in politics or in like a global situation, because normally the enrichment is very much connected to nuclear weapons. Why? So what are we talking when you're talking about enrichment? And that's what comes here that I think is the most important. So now, for now, I've told you about nuclear fuel in general, and I mentioned a couple of times uranium-235. Now here is a small but very important distinction between different types of nuclear fuel. Uranium-235 can generate fission even with no extra energy. So the neutron that comes in doesn't need to bring any energy to make the whole thing unstable and then generate fission. This is good because we know that we need a very low energy neutron for having high probability of a reaction to happen. Uranium-238, which is another isotope of uranium, does not have this property. So it can still give fission, but it needs a very high energy neutron. So you need energy to be brought in. Why this is a problem? Because when you go and mine out uranium, 99.3 is uranium-238, which is the one that doesn't work, and 0.7% is the one that does work. That is why we need to enrich uranium. That basically is to take the normal uranium, take out a bit of uranium-238, and then have at least 2 or 3% of uranium-235. Again, we will see a bit later that, like, in itself, this is a problem only because there is not as much uranium-235, but we see later that there are ways to use also the 238. When we start to go back looking at the nuclear fuel cycle, I told you before that we have a lot of radioactivity problems, and here you see the time scale. So basically, after 10 million years, you still have quite a highly radioactive stuff. That doesn't sound good, but we have a couple of good news. First one, well, the scale on the left axis, that is the measure of radioactivity, is logarithmic. So actually from over there to down here, it's 5 or 6 orders of magnitude less. So it's still radioactive, but much less than it was up there. The second good news is that actually a lot of these products that generate radioactivity, so uranium-238, plutonium, and deuterium, they are actually nuclear fuels. So what we can do is that we can recycle fuel. If we take like the total of the mass of 1 unit of spent fuel, we have that around 92.6% of it is uranium-238, which can either be used again to dilute under normal uranium, or it can simply be used in reactors that can use it as a fuel. And I will talk about them later. Uranium-235 that is left after the fuel has been used, it can still be used. It can basically take out and put into new uranium fuel. Plutonium can also be used because it's also, like uranium-235, can generate easily fission even with no energy in the neutron that comes in. And then what remains is basically like some fission products that have, like they decay in only 100,000 years. So it's quite a short amount of time. Well, it's still better than 10 million. So the idea that we want to have is this kind of fuel cycle with recycle, in which after the nuclear fuel has been used, it is not directly go to disposal, but it is first reprocessed and uranium and plutonium are reused in the cycle. Now, let's go into nuclear power plants. So, boiling water reactors are the first type that we see. It's not the most common today, and especially we are not building many anymore for the future, for some of the reasons that I'm going to say, but still it's the simplest one, so it's the one that makes more sense to start from. We have that the moderator, so what we use to slow down the neutrons is light water. We have a coolant that you need to cool down the bars, which is also light water. And you have the working fluid, which is the water that goes through the Rankine cycle and then expands in the turbine, etc., which is also light water. And it's always the same. So very simple. And you see how it works. So the water that is expanding the turbine, condensed, pumped, and then goes through the reactor vessel. The main problem with boiling water reactors is that okay, well, it's not written there, unfortunately, but it's that basically the water that goes through the reactor gets activated, like nuclear, kind of becomes radioactive, and then brings this radioactivity in all the rest of the plant. So you have basically that this kind of light, but still non-negligible radioactivity is brought around the whole plant, which is bad because it can damage materials, and then when you have to decommission the plant, you have like a huge part of the plant that is radioactive, and that has to be treated as a special material. That's why it has been developed a different type of plant, that is the pressurized water reactor, that we will see in this video, that takes care of that aspect.
The process of creating electricity using nuclear power begins with the splitting of uranium atoms in the reactor. This process, called fission, produces heat. In a pressurized water reactor, the heat from the water surrounding the nuclear fuel is kept under pressure to prevent it from boiling. The hot water is piped from the reactor vessel to a steam generator, where it transfers its heat to boil water and makes steam in a second system. After transferring its energy, the water is pumped back to the reactor vessel to be reused. The non-radioactive steam from the steam generator spins turbines that drive the generator to produce electricity.
Okay, the rest is just the same as before. So as you can see in this case, we again use light water for everything, but the light water that is working fluid is not the same light water that is used as moderator and as coolant. Which means that in that figure, the red and yellow radioactive water stays within the containment of the core, while the blue water, which is like the water that is only used as working fluid, then goes through the turbines and the condenser, and that water is not radioactive. Just something to say about nuclear power plants. Normally, the efficiency of these cycles is very low. We're talking about 30 to 35%. One of the reasons is because, as you've seen here, our reactor vessel is cooled by water. We don't want that water to boil, because if it boils, then it can raise basically, it becomes lower in density, it lowers the heat transfer coefficient, it's a mess. So you don't want that water to boil. So it means that you want water liquid. Even at high pressure, liquid water cannot be at too high temperature. And still, that water, that is like our maximum temperature in the cycle, has to allow for a temperature difference to exchange the heat with the other water cycle. So that's why if this is the typical type of Rankine cycle that you will see in the case of a coal power plant, for instance, this is the one that you see in a nuclear power plant, because your actually temperature source is at constant temperature and at relatively low one. So you're going to have, first of all, it's going to be hard to superheat the steam, so you're going to have like just saturated steam, start to expand, then an intermediate pressure, you reheat it, and then you expand it all over so that you don't have water condensing in the turbine. The result, as I said, is that this is a rather relatively low efficiency cycle. We don't care because, as we said, we don't have much operational expenses because of the fuel. So even if a plant is low efficient, we don't really give a big importance to that. In connection to what I said before, so you can see that the blue part here is pressurized water reactors. The one that I showed you as second is the most common today, and especially the most common that will be built in the future. So out of the 52 reactors that I told that are being built today, 43 are PWR, so pressurized water reactors. You see there like a relatively long list of reactors. We have seen two of them. This one is typically used in Canada and now a bit more in India. It uses heavy water. It's exactly the same as a normal pressurized heavy water reactor, but it uses heavy water as moderator and as coolant. Otherwise, we will not see many other reactors, but just one type. You see that small 2 there, and well, 0.6 megawatt installation. It's fast reactors. So fast reactors are basically the main type of so-called generation 4 reactors, so a future generation of reactors that are, apart from requirements in terms of safety, are also respecting requirements in terms of sustainability. Why? Because fast reactors can use uranium-238 and plutonium and all fuels that normally wouldn't be used on a normal reactor. That means that you have much higher utilization of the fuel, and you have basically very close to no nuclear waste. I will not go into the very details of the physics, it becomes a bit more complicated. What you should know is that basically what happens in these reactors is that the reaction that is important is the second one from the top that you see, is that uranium-238 absorbs a neutron. When it absorbs a neutron, it becomes, after a couple of other reactions, it becomes plutonium-239. That plutonium can generate reactions with a thermal neutron, so with a low energy neutron. So what we can do is that normally we have two types of these reactors. Either we really just want to generate electricity. If that is the case, we simply put in uranium-238 it will be activated, kind of, so it will become plutonium, and then the plutonium will be burned inside the reactor. And that will basically create just a nuclear reactor that can use not only that 0.7% of uranium-235 in the fuel, but the full 100% of the fuel. This is why these reactors can allow a much higher duration of nuclear uranium reserves. The other alternative is that our objective is not to only produce electricity, but to produce plutonium. And we produce plutonium to then use in normal power plants. And that's what we call a breeder plant. A breeder plant is a plant that breeds uranium, so that consumes more, what generates more useful fuel than it actually burns. And the idea is that instead of having many of these expensive and complicated reactors, you have maybe one that then generates the fuel for 10 normal reactors. That is the concept behind it. One of the problems that have been like hindering this technology is also that, well, you are here generating generating plutonium. You know that plutonium cannot be used for other things than for producing energy, and so these are kind of potentially dangerous. So a nuclear, a fast reactor works as a completely different structure, and the idea is that here we don't want to slow down the neutrons, because we actually we need fast neutrons. And to do that, then we need a coolant, and we don't need a moderator, we don't have a moderator anymore, and we need a coolant that is heavy. That's why normally they use liquid sodium as a coolant. It has some good properties, also some bad, in particular the sodium. It reacts in a very energetic form with both water and air. I think that in one case it burns and in the other case it explodes. None of the two is good. But nevertheless, for as much complex and crazy this concept might sound, there are two sodium-cooled reactors currently in operation in Russia. And the second of the two, the BN800, is actually a commercial reactor. Can generate up to 800 megawatt of energy. And two more are being built today, one in India and one in China. And in India particularly, they have an interest in this type of reactors because they have no uranium, but they have thorium, a lot of thorium. And thorium is an element that can be used in the same way as uranium-238. So just to sum it up a bit, like there's a lot of content about these fast reactors. The idea is that they can use the most common fuels as fuel, while normal reactors can't. So we can use this uranium-238, that is, you remember, makes 99.3% of the fuel that we extract. They can not only produce power, but produce more fuel for other reactors, and they can even use the high energy neutrons to transmute, so basically to eliminate, to make inoffensive the waste from other reactors. So this sounds awesome, so why don't we have these types of reactors everywhere? Because they are very expensive to build, they are hard to operate safely. The fuel that they generate is much more expensive still today than natural, so like uranium coming from the mines, and also because of the risk of nuclear proliferation. Okay, last few minutes of the lecture. Where does the cost from nuclear power come from? So, I would like, since you tried before, I'm asking you to try again to calculate the levelized cost of electricity. The equation is more or less the same as Stefano gave you before, and the numbers are there. So take 5 minutes, basically the last 5 minutes of the lecture, to look into, to try to calculate the levelized cost of electricity, and then I will show you the answer that will also bring us back to a bit the discussion that we have made. Okay, so maybe it was a bit of a short time, but since you probably all wish to go for lunch, the answer, ta-da, is supposed to be this one. And I would like you to focus on the fact that for the case of nuclear, you have a very high cost rate of investment and a relatively small one related to fuel, while for the coal, it's rather the opposite. Meaning, again, that explaining once again why the thermodynamic cycle is super much pushed in the coal case and not as much in the nuclear, because in the coal we really want to save fuel and make the cycle more efficient for that reason, while from the nuclear case we don't really care because anyway it's only like that small amount of cost. Yes?
Do we have the costs for the storage for waste here?
So the storage of waste? No. So that is, I mean, I don't think, is it included in the maintenance cost? The cost for waste and storage, waste disposal. Sorry? In the investment cost. Okay. So yes, it is included, but in the investment cost instead. So again, these are the numbers. You have them here, so I don't need to go through them. They are for the project. And final take-home message. So about the fundamentals, nuclear energy is relatively low CO2 and a reliable source of power, but on the other hand, we don't know really what to do with the waste. It's based on the fact that there is a lot of energy in the nucleus, if we basically manage to break it in smaller ones. And when for some types of nuclei, we can do that, but sending a neutron, making the nucleus unstable, and then it breaks apart and generates more neutrons that make the reaction chain possible. Still, we have a problem of fuel cycle because nuclear waste can be acted for as much as 100,000 or even million of years. We can recycle it, but not all, and so that is a very much open question. Most power plants today, when we look at power plants, most of them are based on the Rankine cycle, and and most of the ones installed today are thermal reactors, so they are based on thermal neutrons, and using water as a moderator, and that we have the idea of fast reactors that are very promising for the future because they can make the uranium cycle much more sustainable. Okay, that was it. If you have any questions, feel free to ask. Otherwise, you may go in peace.